Right, so in the previous video we saw how we could integrate those 6 basic rational functions. Right, and those were the 6 ones we had here. And so of course these are particular examples of each possibility, but in general it always works in the same way. Right. So the idea is, if we now take a general rational function, say p of x over q of x, so remember p and q are polynomials. Right. And we're going to assume that the degree of p is less than the degree of q. Right, so the highest power that we have in p has to be less than the highest power we have in q. So if p contains, say, an x to the 5th, then the q must contain at least an x to the 6th or higher. Right. Now, if that's not the case, right, then you're first going to have to do long division, right, and get your expression in the right form. And if you're a bit rusty with long division, then you can look at the long division video that I've posted. Okay. So, how are we going to take this general rational function and write it as terms of these forms, right, a to f? So we want to take p over q and write it, right, as a bunch of terms of the form a to f. Right, so any one of these forms combined. And now how will we do that? Well, first we can note that in each of these forms, a to f, the divisor is irreducible. Right, in other words, we can't factor it any further. Right. So here we have a linear factor, right? Here we have a linear factor repeating 7 times, and then here we have quadratic factors, all of which are irreducible, so you can't factor them any further. And the fundamental theorem of algebra tells us that if we have a polynomial q, then we can always factorize it into irreducible factors. Right, that will either be linear or quadratic, as in these cases. Right, now some of these factors may repeat. So here this quadratic factor repeats 3 times, and here this linear factor repeats 7 times. Right, so that tells us that we can write q as the product of linear and irreducible quadratics. Right, so for instance, we could write q of x as, let's say, a1x plus b1 to the power n, right, and say a2x squared b2x plus c2 to the power n. Right, with this quadratic has to be irreducible. Of course, you could have other linear factors as well, right, and other quadratic factors as well. Right? And this b2 here could be 0, right, in which case you have a term of this form. Right? So, like I said, we could have more linear factors, right, and more quadratic factors, right, but this case is sufficient to illustrate how the technique will work. Right. So, once we factored qx, right, into its irreducible factors, right, then we have a theorem that says the following. And it says that we can write p of x over q of x as a sum, right, so let's say k from 1 to n, right, so that would be, say, dk over a1x plus b1 to the k, right, plus the sum, say, L from 1 to m elx plus fl over a2x squared plus b2x plus c2 to the power L. Right. And essentially, each of the terms we have here, right, are one of these forms, right, which means we can integrate them. Right. So things to note here, right, this linear factor repeats n times. Right. So we're going to have n terms involving this linear factor. Right, so that we're going to have Right, let's just write out the summation so you can see. We'll have d1 over a1x plus b1 plus d2 over a1x plus b1 squared, and so on, up to n. So we'll have dn over a1x plus b1 to the n, right? And similarly for the quadratic factors, right, for this sum. Right. And now once you're in this position, right, so all that now remains to do in order to be able to integrate P over Q is to find the values of the dk's and the ELs and the FLs. Right, so now all we have to do, find the numeric values for all these dk's, ELs, and FLs. Right. And then we'll be able to integrate the expression. Right. So we'll see how to find these constants, right, in the next videos using some examples.